All right, welcome everybody. Welcome, let's get started. So, first off, I just want to say one more time how great those paper presentations were. Now, let's give everybody a round of applause at this. Seriously, I was so impressed. I really appreciate all of you doing those. I think that's a great way to go into some additional technical areas without me having to belabor it in a lecture. And I think it's a different way of learning, which is beneficial. And if you ever go to grad school, do grad school, then reading papers like that is like your bread and butter. It's like part of what you have to do. So good for me, good for you, good for covering more topics in the class. So very well done. So let's cover just a couple of administrative things. The final, Tuesday, 2:30 in this room. Everybody's still planning on coming to the final, right? Okay, good. Also, in case you didn't see the announcement on Piazza, I have changed the due date of the project, just the code though. So your report on the project is still due on Saturday. It's still a 5-page requirement and all of that. What we're really looking for when we grade those is for you to, first of all, show that you understood the project, and also talk to us about some of the challenges that you face, like finding, for just as a random example, finding a particular evidence, the history of one evidence ID. Evidence ID or case ID was hard, and this is how we tackled it. This is how we decided it. Things like that are what we're looking for. So hopefully that is high level enough that you can talk about that kind of thing for 5 pages, even though you haven't finished the code. So that's kind of what I was going for. But again, that's just 20% of your project grade. So, any questions about any of that, or any other big questions before we get started today? All right. Well, let's start into the 142 slide deck then, shall we? There's a lot of transition pages, but still.
Are you going to be recording this question?
Yes, it's recorded. Yeah. Maybe else need the attendance. Well, we'll get it afterwards if you haven't got the attendance. Okay, switching over. All right, let's go back to the very beginning, shall we? To forensics intro. At the very beginning of the semester, we needed to baseline our understanding of what forensics was, right? So, by the way, I've taken out all of the transition like animation, so we'll be able to click through if we need to. Okay. So, what is a computer crime? The big thing is that there are 3 different categories of computer crime: computer assisted, computer specific or targeted, and the third one is computer incidental. So assisted is where the crime being committed is being helped, or it is the computer or digital device is a tool in the commission of a crime. Specific or targeted means that the victim of the crime is a computer. And incidental means that even though it wasn't a tool, it still was the tool of the actual crime. It was used as part of the crime, but only in an incidental way. I probably said that in a really confusing way, but we've talked about this before. Yeah?
So this means the exam is comprehensive, right?
Yes, that's been on the syllabus in February. So yeah, but yes. Yeah. Okay. So basically, computer incidental used to store data related to the criminal activity, but not used to commit the crime. That's how you can tell computer incidental. All right. The objectives of digital forensics, we want to be able to retrieve data from a suspect's hard drive or any other storage media considering that the data might have these difficulties or challenges to actually retrieving and analyzing it. We also want to figure out what happened, when, and who was responsible, right? Because the what tells us the crime that was committed, when gives us a timeline so that we can actually show that they really were there, they were responsible, things like that. And the individual responsible tells us who to go after and charge, submit charges for the crime, whatever it might be. That's the key part on this slide. We want to preserve, identify, extract documents, but we're going to talk about that more when we get to the process. So, understanding digital evidence, digital forensics, again, obtaining and analyzing digital information for use as evidence in civil, criminal, administrative cases. This is just really the definition. The critical condition is that it must be done in accordance with the Fourth Amendment, right? We have to do that, otherwise it will not be admissible in court. So what is the Fourth Amendment? The right of the people to be secure in their persons, houses, papers, and effects against unreasonable searches and seizures shall not be violated, and no warrants shall be issued, but upon probable cause supported by oath of affirmation, and particularly describing the place to be searched and the persons or things to be seized. So we have to have probable cause in order to get a warrant. In the warrant, we have to describe the place to be searched, the persons or things to be seized. And if we don't have those, we cannot do a search or seizure of people, their persons, houses, papers, effects. Those are secure and protected by the Constitution. And on the right is an example of a warrant, in case you've never seen one. Hopefully, never mind. Okay, digital forensics versus data recovery. The difference between these two, what is the big difference between these two? Forensics and recovery. Yeah.
Data recovery.
Yes. In data recovery, the person wants their data back, but in forensics, usually that's not the case. Usually it's a criminal and that data is incriminating to them. So why would they want it to be found? Okay, public versus private sector investigations. I must have put that in the wrong place. Put this one right before that one. So we need to know file system, operating system to be able to do forensics. We also sometimes have to throw things in a hex editor, like when you have a binary file and your instructor is saying it has to be in this format, but your program isn't parsing it correctly, and you have to throw it in a hex editor, right? Okay. Public investigations. The difference between public investigations are always carried out by government agencies. That's what we mean by public. So just like the public sector refers to government organizations, public investigations refer to government investigations. And they are responsible for criminal investigation and prosecution. Public investigation pretty much always means law enforcement. They need to understand some things in addition to what like a private investigation would need to understand, simply because they have to abide by the legal process, whereas a private investigation may not. So a private sector investigation is defined and carried out according to internal policies, right? They're usually conducted in civil cases, can escalate to a criminal case, but not always, just kind of depends on where things go. The guiding principle when carrying out a private sector investigation is that the business operations must not be disrupted by the investigation itself, right? That's critical to this type of investigation. The organization, though, they have to specify what is acceptable use, right? Because if these investigations have to abide by the organization's policy, there has to be a policy in place to begin with, right? So, including what distinguishes private property, company property, all of that. Any questions up to this point? I know I'm going kind of fast, but I don't want to not get to something. All right, let's talk about rules of evidence. So rules of evidence, Who can tell me the 4 rules of evidence? Yeah. Yep. Yes, very good. So, authenticity, admissibility, completeness, and accuracy or reliability. So, authenticity, we want to be able to explicitly link data and an individual. That's the purpose of this rule of evidence. Authenticity just means person linked to data. That's the purpose. Admissibility means we've done everything according to the law, right? We haven't broken any laws. We've done everything by the book. There's no reason that the defense could possibly throw out this piece of evidence because we've done it the way that we're supposed to. Completeness means that we haven't left anything out. Completeness means that the defense can't come and say, well, you know what? There's this time slot between X and Y that might prove that my client is innocent, but you don't have any evidence for it. So how could you possibly say that this evidence is complete? That kind of a thing. Accuracy. What does accuracy refer to? Does it refer to the evidence? What does accuracy in terms of rules of evidence mean? What does it refer to? Yes?
The computer process used to create the evidence?
Yes. So the data that you're analyzing, you have to know how it was created by the program that stored it, right? And you have to be able to show that that process is correct. Biggest and the easiest example for this is timestamps, right? How do you know that the computer really does store timestamps properly? Well, as long as it's set to the correct time zone, and as long as you know those parameters are correct, then you can say, yes, this evidence meets the rule of accuracy, and you might have to explain that. Okay, any questions on the 4 rules of evidence? Okay, closely related to the rules of evidence is the chain of custody, right? So does the chain of custody help us abide by the rules of evidence? Does it?
Yes.
How?
Protects admissibility.
Yes. How?
It holds somebody responsible for the evidence at all points in time.
Yes, very good. So chain of custody, what you do when you have original evidence, you make a copy of it, right? And that copy you work with the copy rather than the original. It's a layer of protection, right? So that copy and the original both have to go into evidence storage, and nobody gets access to it unless it gets logged, right? You know that because of the project. You're sick of all of that detail, right? I'm sure. But you have to know where it was stored, who had access to it and when, what was done to it, and shows that the integrity of the evidence was preserved, because if the original goes into evidence storage and no one ever touches it again, you have some level of assurance that it never changed while it was sitting in the drawer, basically. Okay? All right. So time attributes, we've talked about this a couple times, but time attributes are critical to forensics because they are how we establish a timeline of events. Did I say something funny? No, I didn't mean that in a mean way. Did I say something funny? But sometimes I say stupid things and I want to know if I said something dumb. Okay, so MAC, modify time, access time, change time. These help us know something about the file in terms of its temporal dimension, right? What's its history? How long has it been there? Was it changed recently or accessed recently? That gives us an idea of what happened to that file in the past. Okay, forensic process. Who can tell me what the forensic process is? Yeah, so how do you remember this? How do you remember the forensic process? Huh? Fatima, are you showing off? How do you remember the process? Oh yeah, and then you have to, have to write a report. Okay, very good. Okay, so AAA, acquisition, authentication, and analysis. Makes sense because that's the order that you have to do them in. All right, there's nothing to analyze, which is like the main focus of forensics, right? We can't analyze anything until we have it. So that's acquisition, but then to protect it, we have to authenticate the evidence, and then we can do the analysis, and then we grudgingly do the report because it's the boring part, right? Okay. Any questions on what we've talked about so far? Great. What slide are we on? 27? Buckle in, we gotta go faster. Acquisition. All right, so this is the first step in the forensic process. Basically, it's where you make the copy of the original, right? Purpose authentication. Why do we do authentication? To prove that the copy is the same as the original. Very good. Yeah. Why is that critical? Go ahead, Fatima. Yeah, but why? Yes.
You're doing the analysis on the copy. You want to make sure that it's the same as the original. You're not analyzing what is.
Right, exactly. So if the data has changed, it might have changed to something that is more or less incriminating, right? It's possible. So because you don't want that to happen, you want to make sure that you can prove that it hasn't changed and that it's the same as the original. Message digest is how we do this, right? So we uniquely identify data using the data itself as the source. This is how we do it. We have this infinite input space and a finite output space, relatively small output space. But the key thing about a hash function is that there is no reverse hash function, right? There's no way to go from a relatively small output space to an infinite input space. That just doesn't make any mathematical sense, right? So we have a lossy algorithm, we're losing data, but it's still, we're losing it in a way that can still uniquely, to a degree, identify the input without getting the input through some magic function. Any questions? Hopefully you guys are familiar with hash function. But okay, acquisition types and methods. Basically, we've got two different kinds of acquisition types, right? Static or live acquisition. So you might have heard Mike Maldonado. I can't, for some reason, I can't pronounce his name right now. Didn't get a lot of sleep last night. Sick kids and all, you know. He referred to this as dead disk acquisitions. I don't know if you've heard him say it, but he said that a few different times, dead disk. So that just means you've got a hard drive and you're doing a static acquisition on that disk. This is the preferred method in a lot of cases simply because it's the easiest way to analyze data. But sometimes you can't just rely on this because of encryption or some other aspects of the system. You might need some critical data that's running in RAM. And we've talked about methods of how to actually acquire those, right? With the cold boot attack and some other things, some of the other papers that we discussed. Acquisition methods. These three are also critical pieces of information. So logical. What is logical acquisition? Yes. Yeah, you're targeting very specific files, right? Or file types. So if you're doing, say you're doing a child porn case, it doesn't make sense for you to look into Excel files as much as just looking at all the JPEGs and things like that, right? So something like that. So sparse acquisition. What do you get from sparse acquisition? I want you to tell me what it is. Okay, we're playing it that way. So we get specific files, but we also get unallocated data because our focus is on the partition, not just the file system. So our level of focus has changed from the file system to the partition. So we're taking the partition, which is different from a bitstream copy where the focus is the entire disk or the other storage, meaning wherever it is that it's stored on. It is also referred to as an exact copy or forensic copy, bitstream copy, those all the same. Sure. So two types of bitstream copies. We've got bitstream disk to disk, where we literally get the exact same model of drive as the original. And we make an exact copy from one to the other. The second type of bitstream acquisition is a disk to an image file, where we have a virtual copy, virtual disk image of the original, not a literal copy from one to the exact same kind of model. All right, evidence formats. The most basic one is raw. What is a raw disk image? Yes,
A bunch of bits.
more information.
That's all I got.
It's the uncompressed bit stream of the original disk, right? No compression, no splitting of the, well, I guess you could, yeah. All right. How about proprietary formats? Some of the, well, we kind of worked with some formats. Man, the lab sucked this semester, didn't they? I let the guys in charge know, and they were sad. But at this point, there's nothing they could do other than make a note for next time. Like, thanks a lot. Okay. All right, we got proprietary formats that let us compress, split, and integrate metadata into the image file. But we might not be able to share it between different tools, so that's a shortcut. AFF, why did I throw this in here? I just felt bad because I like Garfinkel. He's good. Simpson Garfinkel, he's my friend. Don't forget that. There's one thing you remember from this course, is that I'm friends with Simpson Garfinkel.
Is that on the test?
Okay, any questions about acquisition before we move on to drives? Cool. All right. Big and little endian. Right. So in case you, sorry, a little tangent, but in case you haven't noticed or seen this on Piazza, for the project, use the native byte encoding for the fields. What?
We have 142 slides, it's best I know, not there.
Okay. Yeah, we only have 100 left. And okay, big endian, most significant byte. Little endian, least significant byte goes first. I hope that you've practiced this because it'll probably be on the exam. Here's an example. So 1, 2, 3, 4, 5, 6, 7, 8. In big endian encoding would be 7, 8, 6, 7, 8, 5, 6, 3, 4, 1, 2. Wow, that's hard to say. This is how, so 1, 2, 3, 4, 5, 6, 7, 8, these should be hex. These are bytes. So I should feel like it's 0x in front of them, but hopefully you can remember. Okay, also please practice this. I really like this as an exam question. It's good, it's easy to write. And it tests several topics all in one. Okay, layers of forensic analysis. Okay, so we talked about all of these layers, right? So once we have a hard disk, we do an analysis on the hard disk to figure out the layout of the sectors on the disk. Once we know that, we can do some volume analysis and discover where the volumes are. And once we know the volumes, then we can start to do file system analysis and actually look at the files. This is the flow that we have to do. You can't just start analyzing files. Why? You don't know where they are. You don't know where they are. You don't know where they start, where they stop, how they're encoded, if they're split, if they're fragmented, any of that, right? Okay. So storage media analysis, I kind of just talked about this. Let's skip over this because we've talked about it before. Okay, hard drive geometry. specifically historic media analysis, head, track, cylinder, sector. Hopefully these are familiar terms to you and that I don't have to reread them to you. Here's this lovely drawing where we got the head actuator right here, head arm right here, the actual head, this little pinpoint right there. This is the disc platter, and it all sits on the chassis. And that will not be on the exam, but it's fun. Okay, sectors, track sectors and clusters. So remember that each of these rings here in this diagram is, yes, yes, it's a cylinder or track. Yes, same thing. Remember, think like a racetrack or a running track where they don't ever overlap. Same thing here, right? Don't ever overlap. You don't. It's not like a record player. It's not like too archaic of a reference. Y'all know how a record works, right? Okay, great. Each of these individual sections are called sectors, and then a group of sectors is called a block, and that term is a little bit overloaded, but the concept is still the same no matter what, which is that it's a group of sectors. So blocks for the disk might be different than blocks for the file system, but the concept is still the same, that a block is a group of sectors. So at the hardware level, the smallest addressable space on a hard drive is what? At the hardware level. Sector. You don't address anything lower than a sector. At the file system level, what's the smallest addressable quantity of space? A block. Please don't forget that. That's like basic units of measurement in forensics, so hard drive geometry, forensics. Okay, all right. We start at 0 for tracks and cylinders. We start at 0 for heads, but for sectors we start at 1 because somebody wanted to make things difficult for teaching forensics. But the first sector has a CHS address of 001. If you want, we can also address them logically, which is the current method of addressing hard drives. Starts at 0, so LDA 0 is CHS 001. And if you want to convert them, you can use this lovely formula. And then here's an example that you should practice with, because I also really like this as an exam question. And I will word the question better this time, for those of you that struggle with it. Whew. Volumes and partitions. Any questions about hard drive geometry? All right, so moving on to volume analysis. A volume is an addressable, a collection of addressable sectors, which is different from a partition. How does a volume and a partition differ from each other? Are they the same thing? Yes.
Partitions are all on the same device and volumes can span multiple devices.
Sorry, say that one more time.
Partitions are all on the same device and volumes can span multiple devices.
Actually, that's not correct.
Is that the opposite way around?
Actually, we need to know.
Okay.
Yeah. Yes. So yes, the distinction there is consecutive. So the reason why is that for partition, and now it's consecutive relative to the volume. So you could have lots of drives and a volume span all of them, and then have partitions inside the volume. Does that make sense? You have multiple partitions inside a volume, you don't have to. It's kind of a tricky concept, but you can. So you understand why you were a little bit off there. Okay. But consecutive sectors, that is the key term for identifying a partition. The purpose of a partition is to organize the layout of a volume, has a starting and ending position, and a type, right? So if we're going to lay out an entire disk, we're going to use what's called the master boot record. An old school version has only 4 partition entries, plus an option to extend, but that's another topic that we never got to. A partition entry has this structure. So, well, this is a partition table. This is a partition entry. So each partition entry is 16 bytes. So we can have up to 4 groups of 16 bytes. Those 16 bytes are laid out like this. So for one partition entry, we're going to have the current state, the beginning heads and cylinder sector type, et cetera, et cetera, et cetera. LBA, a first sector in the partition, number of sectors in the partition. This was the wording here confused people. Hopefully, on the last exam, hopefully you practiced and kind of cleared up the terminology, because I also like this, test this stuff, because you don't know hard drive geometry, it's hard to say that you know forensics. So, okay. Also a really great practice from here to there. These from this 16 bytes. Try to decode it. See if you can do it by hand using a partition entry table. Okay. Any questions about partitions? How are we doing, Robert? All right. Files and directories. So from a user view, a file is a named persistent collection of data, but we also kind of use it to refer to a container. We've got different attributes that a file can have, and metadata, which is data about the data. We talked a lot about metadata, and this is critical for our investigations, right? Directory is just a special kind of data, and different file systems store directories in different ways. The ones we talked about, ext4, it really is just another file, right, in the system, but it has a very specific structure to identify the files that belong to that directory. Links are internal to the file system. They may or may not actually take any space in the file storage area of the file system. Hard links are just, we'll get to hard links later. Okay. Files, any questions about files in the general sense? Yes?
So which one was, I know, pointing to a file name?
Well, I think I have that. I think I have that slide. Because that was very specific to ext4. Like FAT32 does things very differently. So this was like in a high level sense. Yeah. Okay. File system reference model. I really like this model because it separates out the 5 different major parts of a file system and their purposes. Now remember that the application category is just a journal. It's not critical to the function of an actual file system, so we kind of didn't really talk about it. But we need the layout, we need names, we need metadata, and then we need to know where we need to have a place to store the content of the file. Right. So our reference point was ext4, right? We studied ext4 to better understand this model, and layout and size information. This is an ext4 file system. This is the whole thing. Right? No, sorry, they're right here. This is the whole thing, beginning to end. It's split up into block groups. Each block group has the exact same structure and the exact same size, right? We might have some boot code, but that's not too critical. The super block is what has a ton of really important information about layout of and sizes for the whole file system. So, including total number of blocks and number of blocks per group, which are critical for doing all sorts of calculations for where files are and everything, right? This is just there for your reference. Okay, file name category. So we just talked about directories a second ago, but So directory is going to be file type number 2. And the file type number 1 is just a regular file. I probably won't test you on that. This is what a directory entry looks like. This is well, old school, but still, this is cool information. So we've got the inode number, the record length for this file, how long the name is, the file type referring to this table right here, and then the actual file name. So we have dot and double dot, which are special kinds of files, and hopefully you remember that. If we want to delete something, we just increase the record length of the record before it to cover the bytes that would have been taken up by this record. Clear? There's always going to be a multiple of 4 bytes. Yeah. All right. Metadata. Inodes are critical for files for ext4 because it stores. We can have file names point to inodes, and inodes tell us where all the data blocks actually are. Inodes also have tons of metadata in them. It's where ext4 stores 99% of the metadata for every file. Here are some critical fields that we talked about. The 2 interesting ones for us from a forensics standpoint more than any other are the time attributes, which we'll talk about more in a second, but in case you aren't familiar with modes in Unix file systems, this is kind of a crash course on that. We already talked about file types, but yeah, okay, so here's the slide that I promised you with the difference between a hard and a soft link. So a hard link is a file name that points to an inode, and a soft link is an inode that points to a file name. And that's kind of confusing, huh?
That's what we're doing with our make files?
No.
No.
Wait, what are you
I
talking
used
about?
like a -ln command, and I thought it was like creating a soft
Oh,
link.
so yeah, the ln command does create links, yes. So yeah, if you created a symbolic link from your original Python script, for example, you basically gave it a new file name, right? So you create a new inode that pointed back to a different file. So this points to that and that points to this. This only makes sense if you go back to the slides where we talk about what's inside an inode. What's inside the actual symbolic link. So go back to that if this doesn't make sense. Questions though? Okay. We already talked about this. We also talked about this. Okay. 64-bit time values in ext4. Aren't you glad that I didn't require you to follow this encoding scheme for the timestamps in your project? Who's thankful? You're welcome. Yeah. Okay, so the critical thing here is that the original time field goes on the right side. Okay? The reason for that is that if you're going to expand the range of any number by adding bits to it, you can only add it on the left side. Otherwise, it changes the meaning of the original field. You have to add bytes from on this side, which means the extra field goes on the left if you're going to follow this diagram and have it make sense. So we take the last 2 bits of the extra time field to basically quadruple the range of the original time field. All the other 30 bits we take and use as a nanosecond value. This is how you do timestamps in ext4. Questions about this? I see some people with like a sick look on their face. right. Okay. So I need a drink. Hold on. How am I doing, Robert?
Not bad.
Yes, that's what I like to hear. Okay. Content category. So the content is stored by the data blocks. So in order to know which data blocks are available and which inodes are available, we use a block bitmap and inode bitmap to distinguish between those that are available and those that are in use. And those go right here, data block bitmap, inode bitmap, right there at the bottom. Extents. Extents are kind of crazy, but this is how we use multiple blocks. Remember, a block is the smallest unit of space that we address in a file system, right? So if we need more than one block, how do we do it? Extents is the answer for ext4. So we basically say, if this is one block, one data block, we split it up into areas that tell us where the other, actually it's not a data block, this is in the inode, I'm sorry. This is one section of the inode, and it tells us the starting and ending location of the extent, which is nice because previously we listed each of the data block numbers that were part of this file. So to just have starting and ending, assuming if we were to have all of our files be defragmented, like no fragmentation, then all we would need is those two numbers, right? Because if the data is contiguous, we just need the starting and ending number. Easy peasy, ext4 squeezy. Okay, that's an extent. Okay. Drive Slack. Drive Slack's just one of those things you also need to know. So Drive Slack sucks, but it's important. It is the area on the disk that is unallocated, right? But actually doesn't, that is allocated to a file but doesn't store any of the file's data. So the example that we used, what happened? There we go. Whoop. All right, this is the illustration. I'll go back in a second. Is that the blue area is the file contents, and then we have this tan area is the RAM slack, and the pink area that's file slack. So what is file and RAM slack? Drive slack consists of basically divided into the two parts, the file slack and the RAM slack. I got to read this so I don't say it wrong. The part of the drive slack between the end of the file contents and the next block is RAM slack. Everything from that point to the end of the allocated space is file slack. Did I confuse anybody? So, file slack is this is the key. File slack is always going to be a multiple of the disk sector size. Yes.
So is the RAM slack, what you said was that the RAM slack is from the EOF, the end of the block.
Yep, that was wrong. The sector.
Okay,
The end of the sector.
thank you.
I'm getting fatigued. I'm sweating. The AC's out at work since Friday. I've been sick. This is bad circumstances for me to say things accurately. So go by the slide, not by what I said. Okay, so from the EOF to the end of the block. Sector. Man, just go on to the next slide, Mike. Okay. Any questions about Slack or, yes, please.
I don't even know where the end of this sector.
So thank you. I might be able to answer that accurately. So, in this example, we've got 40,000 bytes, right? So 10 blocks times, this is our block size. So 10 blocks of this is a little over 40,000 bytes, right? So if we were to start counting backwards, from the end by the sector size, which is 512, right? Don't forget, how big is a sector? 512 bytes, don't forget. So if we were to start, this is just one method. You could do it a different way too, but if we were to start from the end and say, okay, if we take 512 bytes away from this, have we gone into the file contents yet? No? Okay, then that's part of the file slash. We do that one more time. We take another 512 bytes away from whatever we have left, then yes, we would be into the file. So the end of file there is the RAM slot. Yes?
Just to make sure, again, because we're only allocating enough blocks so that it's like just more than the file, does that mean that our total drive slack will never be one size?
Yes. Yes. Yeah, so to reemphasize that, the size of the drive slack, meaning RAM and file slack together, will never be greater than the block size. So in this case, the blocks are each 4096 bytes. We'll never have 4096 bytes of drive slack. We just wouldn't allocate that block to the file. Yes. That moment was a win. Very good. All right, image forensics. These I'm going to blow through pretty quickly because they're pretty high level and we didn't go into too much. But this talks about the bit depth, which basically means we're going to use more bits. That means we have more data, which means we can have higher quality. This is a color wheel and it's additive. This is how we store RGB values. We use 8 bits for each RGB value, meaning we can go from 0 to 255, put 3 of those together, you get 24 bits. That's one color for one pixel. If you put a bunch of those together, then you'll have a bitmap. And this is just shows how those 3 values from 0 to 255 relate to each other. Excuse me. In case you didn't know, this is how to recognize a graphics file. Vectors graphics. See how I made this smaller so it doesn't look so ugly? Okay. It actually does look kind of like a vector file now. So vector versus raster. Vector graphics are described using geometric shapes that have mathematical formulas. So because you have mathematical formula, you don't get individual pixels painted. You have a line calculated or a curve calculated. And because of that, you can scale it. And sometimes they're called scalable vector graphics. And, okay, so raw file format. This is basically the raw sensor data from a digital camera, which means it may be in a proprietary format and might not be compatible with other cameras. EXIF data is how we store metadata for images. And here's an example. Okay, email forensics. This also, there's not a ton of it to go into, especially since you did an assignment on it. But just as kind of a recap, this is how an email is formatted. We've got a header with a bunch of information that can get added to as it passes from one email server to another, and the body. And of course, you all know how to extract headers from an email because you did that in your assignment. Corporate versus public email. The great thing is about trying to trace a corporate email is that you have standardized named structures. And so it's easier to identify the person. I don't know why you wouldn't have that information somewhere else anyway, but whatever. Blah, blah, blah. And here's some headers. And here's some stuff that we want to look at when we're examining email headers. And you might want to, sorry, I'm starting to get really tired. Okay, any questions about email? Great, so bad. Okay, mobile forensics. We're going to do forensics on mobile devices. What can we get? We can get some stuff from the SIM cards. We can also get tons of like phone book and contact information, sometimes login information like username, passwords. location information, all that stuff is on there. Now, some of the challenges, mobile device has a lot of challenges because of their wireless capability. We have the possibility of the suspect remotely triggering the data wipe or something like that. So there's lots of challenges to protecting that data and its integrity, because we have to be really careful with how we handle it and how we, what signals we allow in and all that. So, but they're basically 3 different acquisition techniques: manual, file system, and physical. So manual is where you just use your finger, you literally use your hand and manually look at stuff, which is really easy but slow. File system, you might plug it into a computer or something and look at the actual file system as it's presented by the operating system, which can be better and do more things in bulk, but you won't be able to recover all the deleted information. And a physical acquisition, basically like a chip off, right? So you take the actual chip off, make a duplicate of the data from that chip, and then analyze it as you would a disk image. Any questions about mobile, friends? Yes.
This is kind of like, but like, so if, say we're forensic investigators, we acquire a phone or something that has a password on it, are we still able to like get information from that phone?
It depends on if it's encrypted with that password. There's lots of it depends. If you get the manufacturer's cooperation, they might know of a backdoor that they put in or something like that. I mean, yeah.
But it does become more difficult.
It does, yeah. Whew. All right, we are on slide 131 and it's 3:52. Just for the record, I'm doing awesome. Okay, let's talk about cloud and web forensics, which is our last topic. Cloud service levels. How many different cloud service types are there? This is a trick question. Lots, right? So these are the basic 3: PaaS, SaaS, IaaS, SaaS, PaaS, LaaS, I don't know. Infrastructure, platform, and software. And this is what all the other services, that's where they started, right? And then other services, things as a service got added on to the collection, right? Actually saw on Twitter in the last couple of weeks, someone, they were like, I spent way too much time on this. It was a periodic table of the Amazon Web Services. It was like a full periodic table too, with the 2 rows at the bottom and everything. And they had categorized them and it was crazy. Color coding, man, giving them each like a 2-character abbreviation. It was nuts. So lots of different types of services out there, not just 3, but these are the basic 3. Deployment methods, don't worry about community. I'm not going to ask you about that. Just putting that in there because it came from the textbook. Public means someone, it's a commercial service. They sell it to you, you buy it. Private means you already have the servers and you install it yourself and maintain it on premises. You are responsible, not another company. And then hybrid is something in between where you have clouds that talk to each other. Your private cloud talks to a public cloud because it has services you don't or don't want to maintain or whatever it might be. And then there's different crimes you can commit that are assisted, targeted, or incidental to the cloud. And then my awesome framework for web forensics. The best part of my dissertation was actually deebling though. That was a lot of fun. This was like the academic exercise that kind of justified it, but deebling, that was good stuff. Okay, what? Yeah, you're de-blinging the Chrome. Yeah. Okay, so here's some unique for web forensic challenges. Rule of completeness is obvious. Trying to do this authentication of associating suspect with online persona, getting access, contextualizing it, all this stuff. But with my framework, it helps a lot because you suddenly have a way to conceptualize and frame everything in so you can get the stuff that you need to and analyze it. Okay, and then just some last considerations for forensic investigations in the cloud. Service level agreements are going to dictate a lot about what you can analyze when you're doing an investigation in the cloud, who's going to help you, the limitations, jurisdiction issues are always going to be a factor when it comes to forensics. Accessibility also, it just, yeah. As far as like technical challenges, there's a lot because you've got lots of different cloud architectures. Collection and authentication are really hard. The analysis of the data is also very hard because how are you going to verify the integrity of the data if you only get one chance to actually acquire it? It's all kind of tricky. There's also anti-forensic techniques. And yes, okay. Do you see the slide number? What slide number is this? Well, hold on, I'm not done yet. I just wanted you to see that. Okay, so you might investigate the actual service provider. You might investigate the customer, and you might investigate locally stored cloud data, each of which are very different in terms of like how you're going to approach them and everything. So, any questions? Yes.
Will phishing and/or malware?
So I have asked SOQUA to prepare some questions on the malware forensics selection that you gave. I think he did send it to me. I haven't taken a look at it yet, but yes, there will be one. There will be one question on malware forensics. I just didn't have a way to throw his slides in here very easily because they were PDF. Good question. But I will probably not ask anything on phishing. Yes?
Study for the final, we should probably still use the original lectures, not this one.
Yeah, so this is what I would do. I would use this to identify areas that maybe I want to go back and review. This is obviously not a comprehensive set of slides. For example, if you want to understand more about symbolic links, that was one area that we talked about today. That if you're not familiar with what's in the symbolic link, that whole this is a link to that and that's a link to this, it'll be confusing to you. So, yes. You thought I wasn't going to make it. I did. All right, well, thanks again so much, and we will see you on Tuesday. Good luck with the project.